In this video, we want to take a look at one-way ANOVA. All right, so once again, we're going to be using the Introduction to Statistics with Python textbook. I'm literally copying and pasting the code from the author's website. Here it is for you if you want to check it out. The book is free to download through the UCF library as long as you're a UCF student. All right, so one-way ANOVA. All right, so ANOVA stands for Analysis of Variance. All right, so what we're going to do, we're going to use the F-test in a special way to determine if the average of two or more different groups within one population have different averages. And we're going to achieve this by, we're going to compare each of the different subgroup variances and their individual averages to figure this out. All right, so in Python, we can either use SciPy stats or we could use stats model. And either one works. There's advantages and disadvantages to both. All right, so let's go ahead and get going. So here we're going to import NumPy, matplotlib.pyplot, SciPy, pandas, URL lib, so that we can get some data, and then we're going to get some stat models and Seaborn for some visualization. Let's go ahead and pull these in. I'm hitting F9 on Spider. All right, so what we want to do first and foremost, I want to give you an idea of why is variance important in statistics. All right, so what we're going to do, let's go ahead and take a look. All right, so I see I have a plot. I have blue, I have red, and I have green. And you can see that the vertical position is different for each of these groups, right? All right, so here we have 5 and maybe 5.3, something like that. And over here we have 4.7 is the overall average for the vertical position of the blue, red, and green. All right, let's look at another group. All right, well here we can see that it's pretty spread out. It goes from 0 to 10 all the way across for all three. And I can't really see what's, it looks like the average is somewhere around 5 for each of them. It looks like probably equal average. I don't know. All right, so let's do this. Let's take a look at this with both sets of dots put on the same graph. All right, so look at the blue line, look at the red line, look at the green line. All right, what you'll notice is that there's when it's a line, that's coming from the group that has smaller variances. The ones that are more dispersed are coming from the groups that had bigger variance from the previous two plots. So here, when they're all tied together, I can tell that there's a difference in their vertical position on average. But when they're all spread out like they are in the more dispersed version, so here's where they're all tied together in this graph. So like this line here, and this line here represents all of these dots, all of these dots, and all of these dots. Now this cloud of dots corresponds to the bigger cloud of dots, of blue dots, not the line. This cloud of red dots corresponds to the bigger cloud of red dots, not the line, not that one. And then this cloud of green dots corresponds to this cloud of green dots that are not part of this line. Okay, so when I look at this, in this format, I can't tell that there's any difference in their averages. In this format, it's very easy to see. And the difference is that I have different variances for the two plots. In this one, the variance, or excuse me, the standard deviation is 0.1. In this one, the standard deviation is 2. So it's 20 times as big. And so analysis of variance, what we're trying to do, we're trying to figure out, can we tell the difference between the average of different populations? In this format, this one, we can't tell the difference. When it's like this, yes, we can tell the difference. and the F-test, the ANOVA test, is how we detect that we know that there is a difference. All right, so when I do ANOVA, my conclusion, if I reject the null hypothesis, is that at least one of the groups is different than the rest in terms of their average. And here we have some data that we're going to download. For us, for this purpose, we don't really care about how we got it. We just care that we have our data. So let's go ahead and pull it up. All right, now we have our data loaded. Very nice. All right, so let's go ahead and, you know what I want to do? I want to take a look at the head of the data. Oh, that did not work out. All right, so here I got an idea what the mean is. Now what we're going to do, we're going to break up our data into 3 groups. So the first group corresponds to those that receive 50% nitrous oxide and 50% oxygen mixture. The second group received 50% nitrous oxide, 50% oxygen mixture only during the operation. And the third group received no nitrous oxide and received 35 to 50% oxygen for 24 hours. Now I'm just reading this from here. So let's go ahead and get our groups. Okay, so now what we want to do, before I can go through and do an ANOVA test, I need to have an assumption about variances. I need to conclude that our variances are equal for this to be a reliable. All right, so here we're going to conclude that the variances are not all equal on this. But we're going to keep on proceeding because we want to, go through the example. I'm going to pretend that it's okay. All right, so now let's go ahead and do one-way ANOVA. So I've got 3 different groups, and it's going to take the average for each of these. It's going to figure out the standard deviation or the variance for each of these, and it's going to figure out does it look like one of these groups is different than the others in terms of their average. Okay, so now let's take a look. What is our p-value? All right, so that's kind of small. All right, so here we are concluding that we are going to reject the null hypothesis in favor of the alternative. We conclude that at least one of the groups has a different central tendency than the rest. Now, ANOVA doesn't tell us which one is the one that's different. It just tells us that one or more are different. So if I had like 100 different populations, I run ANOVA and I reject the null hypothesis, I conclude that one is different than the rest. It might be 2 or 3 or 4 or 5, I don't know. But this tells me that I can go start digging in and try to figure out stuff further. Okay, so now something about this is that this output really didn't give us that much. Got our F statistic and we got our p-value. Now, when you're looking at ANOVA, the bigger the F statistic, the more likely you are to reject the null hypothesis. So if you see a big F statistic, that indicates that you're going to reject the null. There are situations where you can't, because of the assumptions with the F test, if you can't make those assumptions, you can still run this F ratio, but you don't know what the p-values are. A bigger value still indicates that there's a difference, but you don't know how big is big in that situation. All right, so now let's go ahead and let's do ANOVA with a pandas and stats model. So here I'm using pandas to get a data frame. Now I'm going to do ordinary least squares, and I'm going to run ANOVA on the ordinary least squares model. All right, so anytime you're doing regression, you have a direct connection to ANOVA every single time. And every time you do ANOVA, you have a direct connection to regression, believe it or not. So let's see what we get. All right, so you'll notice I get an entire table of numbers. So we can see that for our treatment, we have 2 degrees of freedom. Our sum of squares is over 15,000. Our mean squared error is 7,700. Our F statistic is 3.7, just like we got up here. Our p-value is less than 5, or less than 0.05, and it's the same p-value we got here, rounded off. Our residuals have 19 degrees of freedom. Our sum of squares have just under 40,000, and our mean squared error is just over 2,000. And so one thing that's nice about this is that we get more feedback about our test, and we can see what's going on. The other version just gives us the F statistic and the p-value, and it's left to us to kind of figure out the rest to extract it. I think this is a little bit better. All right, that's all I've got for now. I hope you're staying healthy. Bye.